Mm-hmm. Hey, hi everybody. How do I know if people are hearing us? Yes, I can hear my voice back from the
Okay.
streaming. Okay, so for everybody who's joining this web meetup, as you can see from the screen, we will use Slack for asking questions to the speakers. If you are not on our Slack workspace, you can go on datasciencemilan.org, and if you scroll down at the bottom of the homepage, there is a form where you can type your email address and you will receive an invitation to our Slack. Otherwise, there is a direct link here on the left. You can click on sign in to our Slack workspace that will redirect you to the you will be able to join it directly and log in into the Slack channel. Um, we will wait just a few minutes to let other people joining, and then we will start. Let's wait just a couple of minutes and then we start. All right, Fabio, can we go? Okay, so I'll share my screen. So again, for the people who have just joined the live stream, you can watch the presentation here on YouTube. If you want to ask questions to the speakers, you can join our Slack channel. And the invitation for joining our Slack channel is on the website of datasciencemilan.org. Scroll down to the bottom. There's a form. You type in your email address, and then you receive the invitation. And then on the general channel of our Slack workspace, you will find Luke and I and all the other community members. You can ask questions and start discussions. Okay. We will keep a look at the chat in the YouTube stream just in case somebody cannot join on Slack, wanna interact. If you're not able to join Slack, then you just put your, write your questions either in the chat or in the comments, whatever is more uh, comfortable for you. Okay, dokie. Let's start, and thank you very much for joining to this web meetup. We're gonna talk about serverless machine learning architectures at Helixa. So before we start, let's introduce the speakers. Me, I'm Gian Mario, and probably you may already know me because I'm the founder and one of the organizers of the Data Science Milan community. So not much more to add about myself, but I will let Luke introduce himself.
Hi, I'm Luc Miolet. I'm working here at Helixa as a machine learning engineer, and I'm happy to present to you tonight.
Thank you very much, Luke. What we will cover during the talk today, there are 3 parts, and I will cover the first and the third, and Luke will cover the part in the middle. So we will start by looking into an overview of the services, serverless services available in AWS. Then we'll move into a very deep analysis of the Helix machine learning system. And then we'll finish with a few architectures that can be used for implementing MapReduce algorithms in a serverless fashion. Okay, there are a couple of disclaimers we would like to do. The first one is that what we're going to present today is all based on Amazon Web Services, but 90% of the things you will see, they are reproducible also in other cloud providers. Regarding AWS, there was this conference, annual conference, where Amazon announces all of the changes, the improvements to their services and infrastructure. But this talk was prepared before the conference, so it doesn't really take into account all the recent changes. Okay, so let's start with an overview. What do we mean by serverless? So, serverless is this modern way of building applications without thinking about servers. And in particular, let's make a comparison with the traditional serverless way. In that traditional way, you would ship your code to a server, and then you will manage that server and make sure that the deployment is successful in order to provide the applications. When you do serverless applications, you ship the code, you hand your code to the cloud provider, and then you don't need to worry about which server your code will be executed, because the cloud provider will manage all of this for you and will make sure that the deployment is successful. If we want to do an analogy to understand the philosophy behind, there's this famous thought experiment that says that if a tree falls in a forest and no one is around to hear it, does it make a sound? And some people might argue that since that nobody perceived the sound made by the tree when it falls, then maybe the sound never existed at all. We're not gonna go into this philosophical discussion here, but that is a nice analogy that was used by Winter Clouds for defining what the philosophy of serverless is. That is, if a server runs in the cloud and no one is around to use it, does it need to incur any cost? And the answer is no, you don't have to pay if you're not using that server. And this is the main philosophy behind. What are the serverless services in AWS? Okay, let's talk with some examples. The probably the most common one you will see is the Amazon Lambda, which is like script executions. Fargate is a engine for executing Docker containers. Step Functions is a very popular orchestration service. DynamoDB is a NoSQL key value database. Then there are the queues and the PubSub message services, the API gateway for REST APIs management. And there is Glue Jobs, which is like the serverless version of Spark. And Athena, which is the serverless implementation of Amazon of the REST-DB, which is query analytics engine for running queries on S3 through SQL language. Okay, so those services here represent 90% of the applications built on, with a serverless stack. Let's see an example. So, okay, when we say Lambda function is a script execution, what do we mean? Let's suppose we want to implement a function that lists all of the files in a specific S3 directory. A Lambda function is something that reacts to event objects. So in our case, the event would be a JSON dictionary object that contains the bucket and the path where we want to do the list of the files. Then we have a script, in this example, a Python script, which simply extract the information from the event, and then we'll just run the list of all the files through the S3 API, and we return the paths in the form of a JSON object again. And that execution lasts like half a second, so 500 milliseconds. So if you run this function 1 million times, you will spend $1. So this is the big revolution of serverless, is that you can do like millions of executions and it will cost you on the order of a few dollars. That's really the big innovation. If you building more complex applications where you putting together multiple Lambda functions, then you may want to look into this application framework called serverless.com. That is a hybrid solution, works for multi-clouds, and will remove most of the boilerplate code for building applications with Lambda functions. The benefits are, first of all, that your infrastructure is secure by design because it's all completely managed by the cloud provider. So with all the most advanced security standards, you don't need to manage your own infrastructure and manage the security standards. It is scalable. You can deploy as many functions you want instantly, and you don't need to worry about provisioning, having enough resources to deploy them. It's cheap, as we have seen, it's very cheap. Always available, because Amazon will always find a server somewhere where to run your scripts. Don't need to worry about it. So completely worry-free and very little maintenance. Now we will see why we made the choice of using those serverless architectures in the Helixa market research platform. So in order to give you more context of what the platform does, I will show you some examples. So Helixa is an audience intelligence platform that uses machine learning to provide accurate and timely consumer insights for modern market research. More specifically, I will guide you through an example of the insights that you can get from this platform, so you will understand better. Let's suppose we want to analyze the audience of OpenAI. So we go into our platform, we type OpenAI and say, okay, now give me some insights about these people. And first insight is that this audience is 1.5 million people pick on Twitter. And the demographics of those people are mostly between 18 and 40 years old, mostly male, and located in the United States and in India. In addition to the demographics, we would also provide insights about who are the top influencers. So in this specific case, we can see that there's a very high affinity score with Ben Hamner, who is the CTO and founder of Kaggle, George Hotz, who is a famous hacker who jailbreak the iOS operating system and the PlayStation 3. Francois Chollet is the creator of Keras. And in addition to the influencer, we can also see that who are the top media, in that case, Cephar News, the Hacker News, AngelList, as well as the top products and companies, which of course we will find TensorFlow. Waymo is a startup that is developing self-driving cars, and the Airbnb engineering department. So this is the kind of a use case for the Helixa market research platform. Okay, when we built this platform, we had to satisfy a few requirements. First of all, the whole system has to be able to manage multiple data sets in order to provide accurate insights quickly, real time. When I say real time, I mean just a few seconds. You do the query, you specify what your audience is, and in a few seconds, you want to get the results. It has to be always available, cost effective, because we're a startup, so we want to do things efficiently, with minimum infrastructure maintenance. So as you can see here, there's a very good level of overlapping with the benefits provided by serverless architectures and the requirements we were looking for. So this was one of the reasons why we embraced this serverless paradigm. Now I will give you more, say, technical overview of what is the machine learning system that is behind the platform. Let's start with a look at the end-to-end pipeline. In order to being able to process multiple data sets, the first layer is the data ingestions, where we would convert the source dataset into an abstracted format, which is the common data model, such that all of the downward processes will work in an agnostic way, independently of the data source. So the machine learning jobs will be in order. We will start with content embeddings. When I say content embeddings, I mean text embeddings, picture embeddings, nodes in the graph embeddings. And then we would run the entity resolution to identify what are the real world entities in the data. And those entities are categorized into our proprietary taxonomy. And then we will analyze all of the interaction between the users and the entity in order to construct the digital DNA of the people in our panel. Then from the digital DNA, we can derive all of the missing information. So we can predict all of the missing demographics, all of the missing traits, as well as we can augment all of the observed interest with the latent ones, the ones that we cannot observe, but we can predict using machine learning. And then all of those jobs will will power the real-time analytics applications used by our customers. So the overall architecture for implementing this pipeline will, as we have seen, there must be all of the ETLs that will populate the data lake. Then the machine learning pipeline will read and write from to the data lake, as well as will interact with external machine learning cloud services. And specifically, we use a lot of the Google AI services, such as the language API, the vision API, the knowledge graph. And we implemented a cache in the middle just to make sure that we do not pay more than once for the same request. Then we would also use some pre-trained models from the major TensorFlow and PyTorch hubs. We would use some external APIs for geolocation mapping, and most of the popular machine learning libraries, mainly in Python. The deployment during the pipeline, sorry, we will create models, of course, that we will store into our repository that is implemented with MLflow. And the deployment will be either as a batch job or microservices. When we are done with all this pipeline, we will save the result into the production DB, and that will power the analytics applications. So this is the overall architecture of Helixa system. And in order to implement that, there are a lot of tools for the different stages of the pipeline. And today we are going to see all of them, but the machine learning libraries. The reason is, this talk, we want to focus on how to integrate the models with the wider system. And we will leave how to build machine learning models for a next talk. Okay, so I'm done with the introduction to the machine learning system of Helixa. Now I will pass the ball to my colleague Luke, who will give you very detailed information about the single components of that system.
Okay, thank you so much. Okay, you're still sharing. Okay.
All yours.
Okay, do you see the presentation? Okay. Okay, we are. So, sorry. So first, we're going to talk about the data storage. So most of us are familiar usually with the term data lake and data warehouse. However, today we're going to talk about something kind of hybrid, which is the lake house. So a data lake basically is a place where data scientists will work on unstructured or very raw data. Whereas on the opposite side, a data warehouse will be for mostly business intelligence. It will be highly structured, accessible via SQL queries. So the lake house is something just in between that will accommodate every single user. It's ACID compliant, supports BI, and easily accessible for everyone. So first step in this is to ditch Hadoop. So for those of you who have been using Hadoop, I'm very sorry. The problem with Hadoop is that basically you have your name node and your data nodes. Your name node will manage the data nodes, and the data nodes will manage the loading and the storing of your data. And all of this has to be done on instances, on servers that are always up and running, so EC2 instances, and you need to attach volumes, EBS volumes, that are extremely costly. So all of this architecture usually produces something that is very expensive and always running. So you're paying for a service that you may not be using. We're not always loading and reading constantly data. Sometimes the data is just sitting here waiting. So an alternative, much cheaper, which is elastic, always available and extremely performant, is simply to use S3. So S3, the only limitation compared to Hadoop is basically the maximum file storage, which is limited to 5 terabytes at this point. So this is the first point. So how do we do basically our famous lake house? So we have our data on Amazon S3. We then use glue crawlers that will explore partitions in the data, and every new partition is then added to a catalog, which is then exploitable on Athena, which is the PrestoDB SQL engine of Amazon. So with this, we do several things. such as retrieving the latest version of an artifact. This is very useful when you do batch prediction. So you have your model that was trained, did a bad prediction on a whole lot of, let's say, for users, for example, you want to predict the gender of your users. So you predict them, they're stored in a new artifact. And so just with a view, you have access to the latest version of this artifact. We can also aggregate multiple partitions of the same artifact. So if we don't produce the genders for all of our users at the same time, then what we can do is that we can aggregate them on the same view. So all of our users that were produced in batch 1 with those produced in batch 2, and we can even select the latest version of the gender prediction for every single user. Then we can, of course, do operations that we have traditional on SQL, so filtering, merging. And finally, what we do a lot is exporting snapshots of version views into a Parquet dataset. So how do we work with Glue? How do we work with Glue? So basically, Glue is based on Hive partitioning. So what happens is that in the case of features for users, every time Glue crawlers see folder structures, which is something equals something else, then this will be a key value used to do the partitioning. So here in this case, we have, for the feature store, we have the feature family and the timestamp at which every single feature was created. And of course, we store metadata such that we know later on in the process how this particular timestamp was produced. All of this is stored in Parquet because this enables us to retrieve all of the information that we want for a single user. So we can select, for all of our users the columns in which we are interested. So this is an advantage when working with Athena. Secondly, for the label store, we use a very similar structure. So we have a variable, which is, for example, in the case of our users, the gender, the age, the level of education, and so on. And then we use the second partition is the ground truth, basically. What is the name of this ground truth and the timestamp. For the label management, we use Snorkel, which enables you to aggregate weak labels and train your models using these weak labels. So then we have very similar structure for the prediction. So when you train your model, you ask it to do predictions. These predictions are stored in the variable partition with a certain name and a certain timestamp. So it's very similar, but using all of the structure with Glue enables us later on in the process with Athena to quickly and cost efficiently downsize our data to what we need it to be. Because basically, Athena will go through these partitions in a very inexpensive way. So when you're filtering, you always start by filtering on the values that are within the partition, such that you decrease your cost and your time of calculation. Okay, so now let's talk about how we develop. So after we have our data, we usually have a very simple way of working to test a new model, to iterate on a new model. So we use different tools. For production, there's Amazon SageMaker that will help you with training, model serving, MLflow that will be the model repository that will help you track experiments and also your evaluation metrics. And then for R&D, we also have like tools such as Paperspace, who have a very well integrated deep learning computing environment where you will find most of the most recent packages of TensorFlow, PyTorch, and every other flavor of machine learning you can think about. And then we use also CML and DVC for most of the data versioning and also production of automated reports. So how do we work in terms of research and development? So everything starts by code locally developed on either PyCharm or Visual Studio, which are kind of the most well-known IDE out there for Python. We use Gitflow as a branching model, and we have Jira that describes all of the stories that we are going to work during a sprint. And we use the story number as a reference for our Gitflow branching model. So our code from our local computer is then pushed towards GitHub. And then we connect via SSH onto an EC2 instance that is on the cloud, from which we will pull our GitHub code. And then we can start developing on Jupyter. So the main idea here is that we want our code to be mostly on our code base. We want to do as little as possible on the Jupyter notebook, such that later on we have to spend very few time to just clean up the functions, add tests, and do a couple of lines of documentation. We don't want to spend our time copying code that is within the notebook and then discovering that, oh, there was this variable that we were shadowing. And so all of our experiment is wrong. So the idea is really key. That is really key is have most of your code, if not all as if possible, within your code base. Maintain as little as possible within your Jupyter notebook. This notebook is named the same as the Jira story in order to be easily found. Yeah, as I was saying, we installed the latest version of the code. And all of our notebooks are stored on S3, which enables every person within the team to easily go and check the notebooks. An important part is that we use Alusho as a data cache. So why we do that? So we were talking about serverless, but here we're using EC2 instances, which are not serverless at all. However, we still manage to decrease costs because we use Alusho, which basically will be used as a caching mechanism for most of our data. So we use EC2 instances that are either R4 or R5, so memory optimized instances, on which we will have Alusho and Jupyter started at boot time. We reserve a lot of memory for the caching. We have our S3 buckets that are only mounted in read-only. And what we do is basically we read the data using Dask as if it was within our local system using this caching mechanism. So this is very powerful because in the end we save a lot of money. So if you look at the volume of our data, we have around 1 terabyte of data coming in and out every month, but we only focus on a very small part. But we access it multiple times a day. So we start our day by opening our Jupyter notebook. Maybe the notebook will crash, or we turn it off at lunchtime. We boot it up. We go to a meeting, so we turn off our EC2 instance. Then we turn it on again. We start working again. So that's already 4 or 5 times that you open it a day. And we have 5 people in the team. So overall, if we do all of these calculations, not only do we save time because Alusho speeds up the opening time, it acts as if the data was already on the system. We don't have to go through loading it from S3. We also save money because we don't query S3 to get our data on the EC2 instance. So it also eases up the development because having this data as if it was on a machine locally makes it much easier to write code. You don't have to worry about opening a Boto3 client and how you will have to read the data line by line or managing the Parquet format, etc. So this works well when you're working with small to medium data sets. However, if you have to work with very large data sets, you might have to add a step, which is using Livy and Spark Magic. So the idea is that you will start a cluster, and on this EMR cluster, you will have like 30 instances, and from your EC2 Jupyter notebook, you will connect it using Lively and Spark Magic, and you will send it your queries, and it will return a smaller set of instances. So basically, what you want to do is all of the um, very heavy lifting operations, you delegate them to your EMR cluster. Then you return only a very small subset of the data that you will use for your analysis in your Jupyter notebook. So a couple of recommendations on this part for your EMR notebook booting. So we recommend using memory instance types because they're more practical for our data scientists. They have more memory, and usually this is the biggest limitation for us. Use a dedicated instance as the driver and Spot instances as for the workers. Because thankfully to Spark and HDFS in general, the data and the resources of the calculation on our EMR cluster are resilient to error and will pick up if ever a node crashes or is removed. So using Spot instances mean that they can come in and out of your cluster as you go, and you won't suffer from it. And they will cost you much less. If I'm not wrong, it's a tenth less. So even if you work like on a very large cluster of 30 machines, it might just cost you no more than $5 for an hour of work. Okay, so now let's talk about the deployment. So in terms of deployment, first tool that you need to master are Makefile and Docker. The idea is that these two tools will make everything reproducible and much more easy to rerun later on, to be read by a human also. So what you want to put in your Makefiles is basically a command that has as few arguments as possible. So for example, if you write a Python script with many arguments, your Makefile should contain a line that basically is self-explained on, contains all of the arguments pre-filled for this run that you did. And this, you will push it to GitHub such that it is always present in the memory of your Git, and people can look up and understand your workflow. These are really the basics of your machine learning operations. And of course, Docker for the reproducible environment. So an alternative, if you don't like to use Makefiles, is to use DVC pipelines. So more or less the same idea. It's a Makefile, basically. So now that you've set up the first few components of your machine learning pipeline, the next step are to automate everything using continuous integration. So there are two parts to this. First one is traditional GitHub or CircleCI, and other is CML. So basically the idea is that when you push your code to Git, you want everything to be tested. So for this, you can use either GitHub Actions or you can use CircleCI. And then when you release, what you want to do is build and deploy automatically everything and get some evaluation reports. So for this, you can use, again, for the build and deployment, either CircleCI or GitHub. And for the evaluation reports, you can use CML. So this will ease your workflow and make it basically continuously integrated. You don't have to worry about breaking things because you are protected by GitHub. So just before we were talking about tests, so what tests are we talking about? So of course, everyone I think is knows about unit test. So basically, what we want to do in our machine learning pipelines is mostly be concerned about data ranges and certain predictions. instead of doing the famous assert equal, which is more oriented for DevOps. Sorry. Then we have black box testing for our models. So, for example, you could, if you have a transform model, excuse me. Sorry. You could black box test this model on certain outputs. So you want to control that the outputs are within a certain range. Finally, the end-to-end tests where you have your whole API ready to be contacted, and you can test that the connection works well, that you use dry runs. So dry runs are very powerful, and the idea is that basically you use a very small subset of data to run through all of your pipeline. And if this small subset worked well, then it's a good indicator that with a larger set, it should work well. Okay, so now let's talk about blue-green deployment. So the main tool that will help you in doing this is Terraform. So Terraform, the idea is that you code your infrastructure. So instead of going onto the AWS console and creating resources like DynamoDB, your glue crawlers manually, you codify everything, and everything is deployed on demand by just a simple command of Terraform. And this will help you because basically the idea of blue-green is that you will have your production API, you will deploy a new one on green, and what you will do is you will have this blue infrastructure that is the current one running, and you just have to change the pointer. So on deploy of a new architecture, you just switch pointers, and this enables you to have a very easy rollback, because if something is wrong on green, you just have to switch back to your pointer. This also enables you to do easy A/B testing on your architecture overall. So that's it for blue-green. Okay, so now we're going to talk about different model prediction serving patterns with serverless. So we're going a bit more in the details of serverless. So here we are going to talk mostly about offline training. I'm not going to cover online training. So we're going to look at on-demand with microservices and REST APIs, and batch using AWS Batch. So let's start by batch predictions. So when we talk about batch predictions, we mostly think about we need to predict like the gender of our users. We only need to do it once or once every so often, like say once a month when we have new users coming in. For this particular batch, we need to predict the gender. So what we do in that case, we divide our task into chunks of several gigabytes each. And using Docker, we deploy the task of prediction onto multiple jobs that have the same definition. And then the AWS batch execution controller, sorry, scheduler, will be in charge of deciding which job goes first, depending on priorities, depending on resource allocation, and so on. And finally, once we have the results, they're all put onto S3 buckets, ready to be exploited by our next process. Another model serving method is using microservices. So in that case, we can use two different technologies. So we have ECS on the left and Kubernetes on the right. So we basically have our Docker plus ML flow for the model for deciding which model we're going to deploy. So we can either use Amazon ECS coupled with AWS Fargate, which is a serverless choice because basically Fargate is managed by Amazon. So you don't have to worry about how what's installed. It's just a Docker image that is placed on to this instance. It has some limits though, which are 4 vCPUs and 30 gigabytes of RAM. So if you have bigger requirements, if you need more parallelism or more memory, then you might need to think about going to Kubernetes, which has a serverful choice, which is extremely powerful, but is more costly also on Amazon because you have to you have to manage your own EC2 instances. So it will require more cost on your side and more effort. So you might be wondering in terms of scaling how everything holds up. So as long as we're under the capacity of the provider, everything goes fine. But sometimes it happens that the capacity provision cannot be given by the provider. And this is what happened, for example, with Tesco and John Lewis, another gaming website, just after the announcement of the PlayStation 5. So basically, there was a sudden burst of demand, and the capacity of the system was not high enough and was not able to answer the demand. So people could not complete their order, could not even do the order, in fact. So when you're thinking about scaling to ECS or Kubernetes, you always need to think about these sudden bursts of capacity. If probably they had rescaled the infrastructure just before this release, everything would have been better for them. And of course, there's also the cost of over provisioning, especially in the case of Kubernetes. If you have all of your EC2 instances running and sitting there waiting, doing nothing, then you're paying them essentially for nothing. So this is where probably the serverless ECS would win because you could be able to probably scale down more easily all of these instances. Okay, now we're coming to an interesting use case, which is real-time serverless model serving. And for this, we're going to talk about how can we basically put onto a Lambda an extremely large and fat package, such as TensorFlow. So let's start by the beginning. So we have our training pipeline, which after that we save our model on MLflow. We describe our package requirements, and all of them go onto EFS. Then we update all of our meta information and configurations about this particular model. We do this on a DynamoDB. And finally, we build and deploy our Lambdas. So now, one of your users comes in and does a request. This request goes through the Amazon API gateway, which then triggers a Lambda. This Lambda will check which model to use. It will get the features to be used for this model, grab the model from MLflow, and then it will read the libraries from EFS. So basically, what happened here is that we are using EFS to store very large packages, such as TensorFlow, that do not fit in the requirements of Amazon Lambda layers. So Amazon Lambda have this mechanism of layers that are limited, if I'm not wrong, to 256 megabytes of packages. So basically, if you put pandas, numpy, scipy, you're kind of already nearly at the limit. So adding TensorFlow is impossible. However, you can go over this limitation and by putting your libraries onto a volume that you then attach to your Lambda. This enables you to do a lot of very expensive, very expensive queries using an inexpensive system, which is Lambda. So you can do use very large models, or reasonably large, what fits on a Lambda memory, and do many calls for, as we were saying earlier, for a very, very low price. So once your Lambda has calculated the predictions, then you're done. So if we compare these two paradigms in which we have on one side Docker for batch and ECS, and on the other one Lambdas, there are some differences which are on the horizontal scaling first. So Docker will easily basically, Lambdas will easily scale to on-demand real-time. Basically, if you have a burst of demands, it will fire up very quickly the required number of lambdas and add additional capacity every minute as you need it. However, lambdas have a big limitation, which is in terms of vertical scaling. They're maximum 3 gigabytes of memory and 2 CPUs, and they can run for a maximum of 15 minutes. So long-running tasks that require lots of memories has to be done on Docker. So I would say overall, Docker is, the Docker batch, AWS batch, and ECS ways of thinking are probably easier. However, in the long run, they are more costly. And if you are smart about the way you develop your AWS Lambdas, you can drastically reduce costs. So, it's up to you to pick best of both worlds. If you know the CE dark, I don't know about it. I had to ask about John Mayer, but he said this was a good analogy. Okay, finally, the important part about all of these microservices is that you want to orchestrate them. So Amazon has this serverless step functions, which is an orchestrator, which supports most of your serverless technologies. So Lambdas, Batch, ECS, SQS, SNS. So basically, you can orchestrate anything that is on Amazon via this. It has some limitation. If I'm not wrong, the payload of the step function, so what you communicate in and out of the step function is maximum 512 kilobytes in size. So you have to be very careful with what you leave inside your step function payload. And also you pay by the million, I think it's by the million of calls. So if you have a step function that will produce many lambdas, this will probably cost you more. So you need to be careful with the step functions. So step functions are good when you have to do, let's say, thousands of calls, probably millions. You want to look at something at a different way of orchestrating. Okay, so continuing on our journey of ML ops, just a kind of friendly reminder, even though we're talking about serverless, don't forget your data sanity checks. So when you're having data coming in your models, please check that your data is within the correct range. So if you've heard about Hawaiian Airlines, they charged people $300,000 instead of 300,000 miles. And the issue is that not that they were charging it, is that they were not knowing that they were charging this. It was only after customer complaints that they suddenly discover, oh, we've been doing this. And this is a big issue for our company. They had a lot of issues with their customers, and they had to obviously pay them back. This is something that they could have easily checked by looking at the data distribution. So although we are not talking about a model for this particular case, any model that you're using before you feeding it data, you should check the value range. If you have any kind of anomaly detection that you can add, null values, your data distribution, and there's a couple of tools that can help you that, such as Apache Griffin, Amazon DQ, and a library called Great Expectations. For the logging, in terms of aggregating all of the logging coming from your serverless architecture, you can use the Elk stack, so Logstash, Elasticsearch, and Kibana to aggregate everything into a set of visualization and analysis that will help you understand what is going through your process. So the ins and outs and what are your customers receiving. So this is very important. For monitoring the general infrastructure, you have different tools. So the very basic one is provided by Amazon is CloudWatch, which will help you monitor things such as how much memory your Lambdas have available, how many times they are being fired, how many items are in your queue, how long are they staying, and so on. Then you have Datadog, which is more from monitoring, let's say, serverful architectures. And then you have Funda, which is very oriented to serverless. So choose your flavor and your complexity in function of what you need. Then finally, you need to monitor whatever tool you're using. You need to monitor your KPIs. So what's important in our world, distribution shifts over time. So is my gender model 3 months later using the same features still producing reliable outputs, or is it suddenly saying that everyone is becoming female? Model drifts, utilization, coverage of your tests. So all of this, you want to monitor them within different dashboards, such as Amazon QuickSight and Dash. Okay, so now I will hand back the conversation to the presentation to John Mayo, who will cover this more in details.
Yes, so I will present now. So before we move on, if there are any question, we can just feel free to ask them. Don't have to wait till the end of the talk. Right? In fact, while Luke was presenting, I managed to answer some of those in the YouTube chat. But then we will go through them at the end. But if you have any questions, you can write it either in the YouTube chat or in
Yeah,
Slack.
I forgot to mention, indeed, I'm reading the chat now and I'm seeing that I forgot to mention that in one of my previous slides, I was talking about EFS for the lambdas. And in the reInvent presentation, this limitation is kind of removed now because you can add a Docker image onto your Lambda up to 10 gigabytes. So this architecture has to be reviewed now.
Yeah, correct. You may not need to do the EFS packaging anymore with the Lambda into Dockers. Okay, let's move into the last section of this presentation, which is how do we do, what are the architectures for MapReduce algorithms? So far we presented something that is very specific for of the machine learning system of Helixa, but in general, you may wonder, okay, but how do I implement generic algorithms? And the paradigm that is mostly used is MapReduce. And traditionally, you would use Spark, and we really use Spark. In fact, if you're doing like a big data pipelines, ETL jobs, Spark is really available. But there are some times where you don't want to use Spark, especially for real-time applications, because Spark was not designed really for real-time applications. So plus, having a Spark cluster implies, maintenance. It's true you can use Glue. Glue is a serverless Spark execution, but Glue is very expensive. So what are the other options for implementing MapReduce algorithms in a serverless fashion? So I will start with the simplest form of MapReduce on top of Lambda functions. This framework is called PyVran. PyVran was implemented by the Rice lab. That is the same lab that also implemented Ray and a bunch of other data science tools. And it's pretty simple. What it does is it will create this PyVran executor, and then you, from the driver, which is your local machine from where you're executing this code, you will create a list of input objects X, and then you will specify to the Wren executor the list of input objects and the function. And then the Wren executor will return a list of future objects. So a future object is an object that will eventually give return a result. So when you do future.result, it will stop and will wait for the processing to be completed, and then will return back the object. And the computation will not happen to the driver, but it will be delegated to the Lambda functions in the cloud. So what PyRen does behind the scenes is to doing all of this pickling, serialization and unserialization of objects, triggering all of those Lambda functions, and then retrieving the results back to the driver. And that example is on 10 elements, but imagine that you have millions, okay? You have millions of embarrassingly parallel tasks. You can just use PyRan to say, okay, execute all of those in parallel. I don't need to worry about on which machine to execute that. This is very, let's say, R&D kind of tool. It's not good for production. In fact, when you deploy these jobs with PyRan, it will take you maybe a minute and a half just for setting up all of the infrastructure, all the permissions, deployment, all of the functions, and so on. So it's not very optimized for doing things in more real time. Instead, for more production use cases, you want to use step functions. We have seen previously an example of how you can use step function for building complex workflows with different tasks and integrating different services. In this example here, we are using a very pretty simple flow. That is, we have a driver, then the driver is going to say spin 10 mappers. Each mapper will run some task on its own portion of the data, its own chunk. And then when all of the 10 mappers are done, then we're going to trigger the reduce function. So each block here is a Lambda function. And we will use step function as an orchestrator. Now, that is really beauty and elegant, but there is a limitation that when you execute Lambda function synchronously, you have a limit that now today is 10 concurrent invocations. So we use Lambda because we want to be able to scale, and then we are limited by only 10 concurrent executions of the same Lambda function at the same time. This is really not desirable. So there are different architectures we can use with step function. A common one is to use queues, queue polling, which consists in the submit mappers asynchronously function will spin all of those mappers, but in an asynchronous way. So what does it mean is that when you do synchronously, you wait until the completion, and then you know what the final state of the execution is. When you do asynchronously, you invoke the function, then you immediately return. So then it's up to the driver to check whether that function was successful and when that function is complete. To do that, we can configure our functions to write into a queue as soon as they complete. So the mapper one is finished, and it's going to write the result into the queue. And then we can have a loop here that will check every few seconds. We'll poll the queue, and we'll check that all of the mappers have stored the result into the queue. When all of the mappers have completed, that state is repeated as many times as long as it needs to complete all of them. And then after maybe there's a timeout. If there's a timeout, we'll just go into the job field, or if one of those mappers failed, we'll just go into the job field. Otherwise, we're going to go to the right branch, which is the reducer. Okay, this is also a very elegant way of doing map reduce with Lambda functions and step functions. And there are no limitations on the concurrent invocations, but the limitation is in the state machine here. Because here, every second, we're going to do 3 transitions, because we're going to move from the wait X seconds, we're going to move to the get mapper status, and then mappers complete. So those are 3 different states, and every second we do those 3 transitions. Now, that's fine most of the time, but if the total number of transitions per second is above 1,000, or if the whole full history of transitions is more than 25,000, then the state machine will fail. Like step function is not supposed to work for very long workflows. In that case, we have to use a different design. We have to pull the mapper functions into other external state machines. So we're going to have one outer state machine, which is just the driver. And then the driver will start asynchronously, not directly the Lambda function, but it will start external state machines. So instead of deploying everything to one single graph, we're going to have the state machine just for the mapper. And we're going to invoke that as many times as many mappers we need. And then there's going to be a completely independent one state machine that is the other one that represents the driver. So after the driver creates, so let's say invokes those external state machines, then we'll go into a wait mode. And then we'll wait until the external state machines will send a callback. So when the mapper one is finished, it will send a callback saying, okay, this token that you provided me when you invoked me now is completed, and then I'm giving you back. And so the outer state machine will just wait for collecting all of those callbacks. And then when all the callbacks tokens are collected, we can consider that all the mappers were executed. And this architecture here has no limits at all. It's also very commonly used for example, for validation checks, because let's suppose you're, as part of your workflow, you have to check whether a person has enough money in his balance account. Then you won't be able to implement that into your own function, into the AWS infrastructure. So maybe you need to delegate an external service, and you don't know when that service will actually complete. So you don't want to be stuck and wait for that service to respond. So this is a pattern you can use. You send a token, you wait, and then you just, when the callback arrives, then you move on. If the callback does not arrive, then you can consider it failed after a certain timeout. But step functions is not the only way to implement MapReduce algorithms. In fact, AWS recommends this architecture here that is made of events. It's a complete event-driven architecture. There's no step function, there's no orchestrator here. It's all completely distributed, event-driven. So the way it works is the driver will start the workflow saying, okay, this is an input path in S3. Then for each file in this folder, please execute this mapper function. Then the mapper function don't communicate with each other directly, nor with an orchestrator. But what they do is they will save the results into the output directory, and we can register that particular output directory to trigger S3 events. So every time you add a file, it will create an S3 event. And then there's going to be a coordinator Lambda function that will react at each one of those events. And the coordinator function will simply check that all of the output files have been saved into the output directory, because the coordinator knows that there are 10 mappers, for instance. So it will expect to see 10 files into the output directory. When that happens, then the coordinator can trigger the reducer steps, and so on. So this is another way to MapReduce. But I personally do not recommend that because I find it very hacky. This way of triggering events, it relies on side effects on the I/O, and I don't really like that. I prefer to be more in control of the algorithm. I don't want that the execution of those functions depends on side effects of writing into a particular directory. I really want to be more in control. So a similar architecture can be implemented using DynamoDB. So at Helixa, we have a special DynamoDB table that is the job tables, the jobs table. The job table has one identifier for the job ID, and then each job ID is made of different tasks. So we have the job ID, task ID, which is in this example, we have an init function, init task, map1, map2, reduce. When you want to execute that job, you will populate this table with an initial status of submitted. And then we can specify what the task type is, because most of them is Lambda functions, but nothing really stops you for executing tasks through containers, for example, in an AWS batch, for instance. The most important part is the task dependencies. Here we are creating our own direct acyclical graph, all the dependencies. We make sure there are no deadlocks. And what we're saying is that init can start straight away, but the map1 and map2 functions requires init to be completed first, and reduce function requires map1 and map2 to be completed first. And the function name is simply the name of the function that was created before, and the payload is what we're going to provide as an input to the as an event input to the function. Now let's see how that works. So imagine you want to execute this job, so you populate this table, you put all of those rows, and then that will trigger an event that the table has changed, like some mutation happens, some new elements were inserted. So the coordinator will react and will go through the table, will look for all the tasks that are still in a submitted status, check if there is any task that the dependencies have been solved, and then we'll execute them. And then when the init function is completed, we'll update the status, and that update will trigger again the coordinator, which will scan again the open task and trigger the ones that now have been satisfied in terms of dependencies. And you continue that to the reduce step, and then when the reduce is completed, the last trigger of the coordinator will check that all the tasks are completed, and now we can send a callback to the entry point. This is a very, I would say, elegant and advanced way of controlling the execution without going through an orchestrator. Okay, so we are finished with the last section. Let's do some final remarks to recap everything we have seen today. I think the first thing that we all have realized is that machine learning code for the models is actually only a tiny bit, tiny fraction of the complexity of the wider system. So the infrastructure is vast and complex for making a machine learning model to be integrated into an enterprise product. And you should really be careful on not falling into a trap where you have the temptation that you want to implement things, so you want to move fast because you want to innovate, you want to get out this new model into this new feature, and you realize that the infrastructure is very complex. So you may think that you are justified to move fast and break things, and maybe I'll fix that later. Now we have to really deliver that feature. That is really bad strategy in the long run. It will hurt your business. And my recommendation is that you always want to make sure that, yes, you want to move fast. In fact, Facebook changed their motto in 2014, but with stable infrastructure. And it is possible. Today, we have seen a bunch of tools. We have seen a few architectures. We've seen some engineering practices. They may not apply to your use cases, but I hope that you learned something, and they inspired you for your the infrastructure you're about to build, or the ones you already built, and maybe now you got some new ideas. And also, if you never adopted the serverless technologies before, I think this is a really good time to start, because the technologies are really mature. Especially if you're in Amazon, AWS, all the serverless stuff is really mature, but also in the other cloud providers, like Google has their own set of serverless services. So really check this out. It's a really cool technology. Okay, so if you, moreover, if you want to learn more about all the different aspects of building machine learning products, like customer-facing machine learning products, you can go on the Helixa website and you can download this non-technical guide that will cover a bunch of topics that we didn't cover today. And this is it for me. So I will leave Luke the last word on the amazing people that Helixa is looking for at the moment.
Yes,
You can
so
tell
we're
more
looking
about
for someone to join us at the moment. So if you're interested in deploying machine learning models to production and you are willing to learn about cloud, code optimization, and serverless technologies, then you are more than welcome. We're looking for someone who has at least a bachelor degree or above in software IT, who knows his PyData stack, so Pandas, NumPy, SciPy, and so on, has basic knowledge of SQL, as you can guess from the talk of today, it's very important. And finally, who has a basic understanding of machine learning concepts. So it's more of a, I say, operative person that we're looking for. So if you're interested in this kind of role, please feel free to contact me at my email, lmule@helixa.ai.
Thank you very much, Luke. And I think we're done for today. Let's see if there are any other questions. So don't be shy, guys. Someone is typing in Slack. Meanwhile, Luke, why don't we go through the questions in the chat, see if we can provide good answers now. So Steve asked, AWS has pretty stringent size limitations for Lambda functions. How do you manage to deploy state-of-the-art deep learning models that occupy hundreds of megabytes in ONNX, PB, PTH format, and so on? So I think, Luke, you maybe you want to recap this answer you mentioned before.
Yeah, so of course, you need Lambda cannot work with everything. So the limitation that I was talking about earlier on the Lambda service was mostly about like packages like TensorFlow, who occupy a lot of space on disk, but you don't need to have all TensorFlow running at the same time. Um, when you're talking about very large models, then obviously Lambdas is not, I think, the best candidate for this use case. You likely need to go up to batch. We've also done it with Spark, so PySpark, so using multiple runners to get um, models to produce the answers in a more timely fashion. I don't know if you have anything to add on this, John Meyer.
Yeah, I think there's also another consideration we can do is that in the, let me see if I can find the slide. So deployment, where was it? Yeah, there you go. So when we do real-time serverless model serving, yeah, the okay, we are getting the model from MLflow at runtime, but if the model is not too huge, or better, if the model is not doesn't change much often, like you deploying like a new model every, I don't know, like continuous learning kind of modeling. If the model is static and you only update it once in a while, you can also think of packaging the Lambda with the model inside. That will save you all of the IO of asking MLflow to get you the model at each single request. So you can have the Lambda function already packed with the model, and the packaging can, if you can fit within the 250 megabytes, fine. Otherwise, you can use the Docker container with the model embedded inside, or the old-fashioned way with the EFS. And then there was Amin that was asking if S3 and Dynamo can be linked by lambdas, and I think this is that was exactly what we've seen in the last slides of the MapReduce algorithms. In Amazon, almost everything can be linked to Lambda. Like every every action, everything that happens in the Amazon cloud will create events, and you can register Lambda functions to react to events.
I see also on the chat, Ricardo asked about how much money we saved. So basically, recently we reworked our platform. So let's say we have two different platforms. One that we will call US only, which is the old platform, which is serverful. And we have the new one, which is mostly serverless. And basically, every week on production, we pay $80 to produce let's say, in a serverless way, the data. I don't think we've ever fired as many lambdas required on the Insights engine to basically pay more than $5 per month. So overall, we save tens of thousands of dollars due to that. Because on the other hand, the whole platform is completely serverful. It requires very large machines to be constantly available. So we had to buy reserved instances on Amazon for 1 or 3 years. So this costs, even if we save a bit of money on the 3-year run, still it costs a lot, and it's not something that we want to do overall. I think now we will never go back to a serverful model in any of our new developments.
Yeah, I would say that if you, as a company, can afford to have a dedicated infrastructure team that is on call and then do all the optimizations of the case and have your own infrastructure, um, it might pay off. It might. I still not convinced. I would still go for serverless, but I see a lot of companies they prefer to build their own infrastructure and maintain them with dedicated teams of engineers working full time just on the infrastructure side. We are a startup, so we didn't have that choice. Like if you want to invest, we rather would invest in hiring data scientists and machine learning engineers and building amazing algorithms rather than investing a lot just in infrastructure when we have the cloud provider that can do all of that for us. We don't need to worry about anything, and at the end of the month we would see like $10,000 of savings. So it's hard to think about one reason to not do that. And then Ricardo also asked another question, that is this architecture allowing to handle big models such as BERT base? Luke, what do you think?
Yeah, I mean, we use such models in the past, such very large models. So the main limitation, as we said earlier, is what can fit on the EFS volume, basically, on the EFS or on the Docker now. Then if it cannot fit, you have, of course, to go to more of a Docker solution using either AWS Batch or ECS or Kubernetes, depending on your on the way you want to serve the model. But still,
Right.
serverless is completely possible.
Yeah, don't confuse serverless with Lambda functions. I mean, Lambda function is just one way of doing serverless things. Maybe one limitation could be when you load in memory the RAM, you can only have 3 GB. So if the model is really huge, like gigabytes, then you have to load it in memory in order to do the inference. That might be a limitation. Or if you want to do inference on GPUs, I think it's not possible to do lambdas on GPUs. So there might be cases where you do not want to use lambda for model inference, and you want to have your own Docker container. But even if you have Docker container, you can still do the serverless Docker container inference version of it. Like SageMaker is actually a serverless way of doing doing inference. The only thing with SageMaker that's very pricey. If instead you build your own custom thing using Fargate, there's not much to really configure or manage because Fargate it's scales. It's just like Lambda functions for Docker containers. And then you have 30 gigabytes. If you need more than 30 gigabytes to do model inference, then I think this is not a, a real-time inference. Probably is some more bad job.
Yeah. There's also a question about from Amin about EC2 Hibernate. So if you're using Hibernate, you're basically putting in sleep your instance. The thing is, you still have to manage all of your infrastructure, and that's not something we want to do. Basically, that's an added cost in terms of human resources and time to spend for us. So when you're a startup, the least resources you have to manage, the better you are. You can spend more time on developing features and your product rather than on managing your infrastructure.
Yeah, I agree. Let's see if there's another question. Somebody was worrying that was too much Amazon-centric, and yes, it is. EL, don't know what EL stands for, but it's person asked if that can be used outside of Amazon. And I think the key takeaways today is more on, well, first of all, the engineering practices, they don't depend on the specific tool. And the methodology of thinking about functions like really micro, like mini, like nano functions, nano services, okay, very small microservices made of a lot of functions. I'm quite sure that you can do that in every cloud with any cloud provider. Yes, they're gonna have different APIs. Let's see. And then there's a last question from Amin. Again, he asking, can we split one runtime of more than 15 minutes on multiple lambdas that are less than 15 minutes with triggers and use API gateway caching mechanism and throttling to serve our models? Luke, any insight on that?
Mm, well, I mean, I haven't used the caching mechanism of Gateway, but I think the issue here is that you would first need to produce all of results. So I don't know what is the limitation on Gateway on the caching, how much you can cache. So I think it really depends on the size of your predictions, of the output of your basically of your payload of your lambda. Anyway, in terms of caching, usually it's better if you can go to S3 because at least it's resilient, I think. I don't know if you want to add anything, any clarification on this point, John Mario.
I'm not big expert of API gateway. Uh, Generally, this is the part that the data engineers and the backend engineers take care of. But I can tell you that it is possible using step functions, where in step function you can just chain different lambda functions. So you can ask your lambda, you can implement your own, let's say, resume mechanism where you maybe I give you a bunch of things to do to a single lambda, and the lambda will save the intermediate results as it process. And then when you resume, you can just start from the last checkpoint. If that is the case, I don't see why not run. I mean, if you have to process 1,000 things, why not running 1,000 lambdas? And if you really can chunk your work in a very little, if you can resume your work, it means you can split it. If you can split it, then you should run a lot of different lambda functions independently, or one after the other, orchestrated with step functions. Regarding the caching, in the step function, by default, I think this is not even possible to disable, is the caching mechanism on the input object. So step function works with, just like lambdas with objects, like JSON objects. So this is the event that will get propagated through the whole state machine workflow. And that event is the request. If you making the same request twice, the cache works, I think, for 90 days. So it will not re-execute the state machine the state machine if the hashing of the input object input event is already in the cache in the last 90 days. If that answers. All right, I don't see any other questions coming. So I would say thank you very much, everybody, for participating tonight. And thank you very much, Luke.
Thank you for inviting me.
You're welcome. You're welcome anytime. And you want to give us updates about the new architectures, Helixa.
Sure.
And I'll guess that I'll see you guys. We will see you at the next event that is going to be on January, and it will cover machine learning design patterns. We sent an email to the mailing list with a survey where you can pick which ones are your most favorite machine learning design patterns we will cover in the next talk. If you didn't receive the email, you can go to the meetup page of Data Science Milan, and you will find the conversation here, Meetup Data Science Milan, and you will find the conversation in the not the discussions, but in the hey, bear with me, message boards. You go to the message board on our Meetup page. There is this discussion. Choose your favorite machine learning design patterns for the next event. We will have Michael Munn, who is the author of this book about machine learning design patterns. And if you follow the link, you can go to the Google form where you can vote which ones you want to be covered in the next event. That's it. And thank you very much. See you next time.
Thank you very much.